So just to reiterate again, in this coefficients table, we have all the information about the inferential statistics associated to these terms that we're working with, the intercept term for our regression, the slope term for the regression, and remember secretly the correlation that's associated with our two variables. We primarily look at the hypothesis test outputs for the slope, right? This also gives us whether or not we have a significant correlation. So now at this point, we should have everything marked up with some nice comments. We should have grayed out stuff that we can kind of ignore, at least for the purposes of this class. There's only a couple of things that we haven't addressed. And primarily they're what I call these diagnostic plots that are off to the side, this normal probability plot and this residual plot. And so I want to talk about those next. If you'll remember from a few weeks ago, when we were talking about confidence intervals and hypothesis testing, I gave you a couple of precautionary notes. There are certain situations where you shouldn't trust the results of a confidence interval because violating certain assumptions ruins essentially the inferential statistics behind that estimate. And what happens is you can get a confidence interval where the success rate of that process is actually much lower than the confidence level that you're setting. Similarly, your hypothesis tests kind of run the same risks. Now, as we've been talking about, our Excel regression, now as we've discussed so far, there's a lot of inferential statistics involved in a regression analysis, right? Based on a sample estimate for intercept and slope, and even a sample estimate for your correlation coefficient. We're trying to say something about what happens at the population level. Now, our ability to say something confidently from a sample lifting up to the population level does require that we satisfy a certain set of assumptions. And the way that we test whether these assumptions hold is by using these diagnostic plots, the residual plot and the normal probability plot. Now, don't want to get into too much detail, but I do want to tell you what a good residual plot would look like and give you some examples of bad ones. And I want to tell you what a good normal probability plot should look like and give you some examples of bad ones. So basically, the idea here is when you run a regression analysis, you should know what to look for. Is this a good or bad residual plot? Is this a good or bad normal probability plot? And if they look bad, go and seek some help from a statistician or somebody who has a little bit more experience with regression modeling. Okay? In terms of what a residual plot actually is, it's nothing too fancy. It essentially just plots the predicted values down on the x-axis. So these were the predictions made by the linear regression. And then the y-axis is how big was the mistake, or what was the residual. And essentially what you're looking for out of a good residual plot is that there should be no discernible pattern. It should kind of look like you just threw a bunch of thumbtacks at the wall and whatever stuck, right? So they should be generally grouped toward the center of the plot, but there really shouldn't be any discernible pattern. So this is really a very visual thing. So I'm gonna walk you through a couple of pictures, and then I'm gonna show you how this works through another R simulation. So this is an example of a very good residual plot, right? Again, just looks like some random scatter. This is an example of a bad residual plot. See how there's a lot of kind of grouping below this zero line? And it seems kind of more spread out above. There's more of a discernible pattern for the way that the linear model is making predictions, right? We can see that it tends to make a lot of negative mistakes, and the positive mistakes have quite a lot of variation associated. Here's another classically bad-looking residual plot. This is something, the fancy term for it is homoscedasticity. One of the assumptions is that in that no discernible pattern, we see about the same amount of variation in our residuals sort of up and down. And we can see that there's not a lot of mistakes on these smaller predicted values, but there's quite a big range of mistakes on the larger predicted values. So we don't have what we call constant variance. So this is another bad looking residual plot, and this is where you might want to go seek a little bit of extra help in your regression modeling if you start to see a residual plot like this. All right, so again, just a quick review. Random scatter is good for a residual plot. This means you're all good to go. It looks like most of your assumptions are met. But once you start being able to describe a pattern in the residuals, then you might want to hit the brakes. You might want to hit the pause button. Okay? Let's take a look. Here's another one. We can kind of see that on the lower and the higher values, right, our residuals tend to be positive, but in the middle, they tend to be negative. This is, as we'll see in a second, will be kind of indicative of a nonlinear relationship trying to be mapped using a line. All right, so let's look at a quick R simulation, and I'll show you some sort of good and bad situations with these residual plots, as well as the original scatter plot and the regression line. So here's our simulation. I can change the sample size, and I can grab new samples. And as far as the different shapes that I could choose, I'm going to pick a situation where the regression is good, the assumptions that we need for the regression are satisfied, and then I'll show you an unequal variance example and a bad linear fit example. So let's start with the good regression. Let's pick a sample size of maybe 55. Right, you can see that over on the left here we have our scatter plot with the regression line in red. Right, and then on the right we have the corresponding residual plot for that particular sample. And what you can see here is essentially this is an example of a very nice regression properly applied. The line kind of cuts right through the middle, which leads to errors that are kind of randomly scattered about this zero line. And there's no real discernible pattern. And even if I just kind of generate some other random examples here, you'll see that in all of these cases where the regression is properly applied, the assumptions are met, the residual plots to the side don't show any type of discernible pattern. They just look like random scatter. Somebody dropped a bunch of marbles on the floor. Now here's an example where there's a bad linear fit. The relationship for this data is actually exponential. We see a pretty obvious curve, but we're trying to model it using a linear relationship. So this is a bad, what we call a bad linear fit. Linear regression wouldn't be a good model for this particular situation. And what you can see, not only does the line not really follow the dots, but in the residuals, you see kind of a nice discernible pattern, one that we mentioned before. On the smaller values, our line is tending here to make positive errors, which essentially means the line is under-predicting the actual output values. In the middle, it's over-predicting, leading to negative errors. And then towards the other end, it's, again, under-predicting. And you can see that even with new samples, this general trend kind of stays the same. Okay, so when you start to see a pattern in your residuals, you can kind of link it back to maybe the line is not the best model for this particular data. The last one I'll talk about is this unequal variances example. Maybe I'll increase my sample size so you can see this a little bit more clearly. But in this case, is one of the violations here, or one of the assumptions that we need, is for the variation of the dots away from the regression line should be about the same for the smaller values as well as the upper values. But what we see in this particular case is with the residual plot, there's some, but not a lot of variation down on these lower values. And when we get to the bigger values, we start to see much wider swings. Okay, so this is a violation of our assumption that the variation should be equal. And even as we collect different samples, we see that this type of relationship is always kind of highlighted with our residual plot. So let's jump back to our example. Taking a quick look at our residual plot, maybe I'll make it a square so it's a little bit easier to see here. Move my normal probability plot to the side. Oops, deal with that later. Again, this sort of looks like random scatter. There's no discernible pattern. We've got above and below errors with, again, no discernible pattern to why it goes above and below. So this is a good looking residual plot. It seems like the assumptions that we need to meet and that are checked by this residual plot are met. So our next thing we're going to do is start to think about our normal probability plot. The normal probability plot, or sometimes called the normal quantile plot, is pretty easy to interpret, right? In the best case, it should look like a nice line, right? So there shouldn't be any bend on either end or in the middle. And let's take a look at a quick R simulation showing you some good normal quantile plots and some bad ones. So one of the assumptions that the normal quantile plot is testing is that the residuals, so the mistakes that our linear prediction tends to make, should have, typically speaking, a normal distribution. Okay, so what that does is it takes your residuals and it creates what we call a normal quantile plot. So what the normal quantile plot does is it kind of maps the sample percentiles against theoretical percentiles if that data were normally distributed. And in the case that it does match a nice normal distribution, what we should see is that these dots tend to follow a nice line. All right, so in this case, I can choose different shapes for my residuals, positively skewed residuals, negative, uniform, bimodal, etc. I'm going to start with normal. I'm going to kick my sample size up. And the point I want to make here is that these will loosely follow a line. So even when I know I have a normal shape, and I can get some new samples here, right? Since this is coming from random data, right, your shape's not going to be perfectly normal, nor are these dots going to perfectly follow a line. But if they more or less kind of follow this line, we would assume that that assumption is met, right? So we do have a little bit of flexibility in this. There are some patterns that you might start to notice. So for example, if your residuals are positively skewed, or in this case, I think we were calling it right skewed, so you kind of see the bulk of your stuff off to the left with the trail off to the right. This is what your normal probability plot ends up looking like. It's kind of U-shaped, and what you see is like sort of a bend in the middle with a trend kind of moving upwards. And if you switch to left skewed data, it looks the other way. The bend is now more of coming up to the top of a hill, kind of like this. Uniform and bimodal data can look very strange. They're sort of S-shaped curves, right, in your normal quantile plots. And so if you see any of those types of patterns occur, you may be violating that normal residual requirement. So if it doesn't look like they're more or less, aside from a little bit of variation, like they're more or less following a nice straight line, you might want to have this checked out by somebody who's a little bit more well-versed with regression analysis. But that's what we're looking for. We just want our normal quantile plot to be a collection of dots which are more or less following a line. And if we take a look at our normal probability plot, normal quantile plot for this data, for this regression model, again, we see a little bit of variation up, down, etc., but this looks like more or less these things are following a nice line. This looks like a nice normal probability plot. So based on these two diagnostics, the residual plot looks good, the normal probability plot looks good. We should be able to trust pretty well the inferential statistics associated with this regression analysis. In other words, right, this confidence interval estimate should have about a success rate of 97%. And for the hypothesis testing, we can trust these p-values and the conclusions of our test. Okay, so as a quick overview of this example, we were interested in the relationship between age and maximum heart rate. Specifically, we want to use someone's age to predict their maximum heart rate. So we can fit a linear regression based on this sample data. And not only can we talk about their correlation, what the slope term, what the intercept term is, etc., we can visualize this, but now with the data analysis tool pack, we can actually add on a new layer of inferential statistics to this. So based on these sample estimates, we can do hypothesis testing for whether the intercept at the population level is 0, or whether the slope term at the population level is 0, which corresponds and actually simultaneously tests whether the correlation at the population level is 0. Moreover, this will compute confidence interval estimates for what the slope and intercept terms, again at the population level, will be with a predetermined by you as the researcher level of confidence that you want for that confidence interval. So now we know, all right, well, the sample suggests that the intercept is 215, which, according to the sample size, etc., would suggest that at the population level, we can be 97% confident the true intercept is between 207 and 224. Our sample suggests that the slope is a negative 0.97, but we can conclude from our analysis that at the population level, we're dealing with a population level slope term between negative 1.2 and negative 0.75. We can trust these inferential results because when we checked our residual plot and our normal probability plot, both of them sort of passed what diagnostically we're looking for. The residual plot looked like random scatter, and the normal probability plot, more or less, we had the dots following a nice straight line, with no big bends or S-shaped curves associated. So this is what we've added to our new level of regression analysis.